Today we will see in detail the Heisenberg uncertainty principle. That is a generalized Heisenberg uncertainty principle and the proof for the same. Heisenberg uncertainty principle says you cannot measure any two canonically conjugated parameter accurately simultaneously. That is more important. You cannot measure accurately simultaneously. Uh, Say for example, delta x into delta p is equal to or greater than h cross by 2. That is error involved in the measurement of position multiplied with the error involved in the measurement of momentum must uh, must be equal to or greater than h cross by 2. So this is the error in position. This is the error in momentum. Uh, X and P are canonically conjugated parameters. Similarly, energy and time you cannot measure accurately. So that is a error in energy multiplied with the error in time is equal to or greater than h cross by 2. In general, it can be written as, let us say, A, B are the two operators. Delta A, that is error in parameter A and error in parameter P. Delta A into delta B is equal to or greater than 1 over 2 modulus modulus the expectation value of the operator X and P. So this is the generalized expression. We will see the first one and I will explain the first one in detail. Uh, Let us say that delta x we are going to measure the position. See, there is one particle. I am going to measure this position accurately. So in order to measure this position accurately, I got to use the light, a light of wavelength less than this size of the particle. Then only I can make a accurate measurement. That is lower wavelength means higher frequency. That means high energy. When you are shining the light, in order to measure the position of the particle, when you are shining the light, it will get some energy from that light and it will move on. It will get some momentum. So, uh, so at that time, the momentum gets changed. If you want to measure the position accurately, there may be the error in momentum. You cannot measure both simultaneously. In order to measure the position, after some time, you measure the position of the particle and usual. If you know the initial condition, velocity, and the other thing, you can find the momentum. But you cannot measure both the parameter accurately and simultaneously. Same thing I can explain using this simple diagram. Let us take a sine wave of fixed frequency like this one. Here it is interesting that since it's a fixed frequency, energy will be the same. That is h cross omega. H cross omega energy is same fixed. That means energy is equal to p squared over 2m. Momentum is fixed. In this case, momentum is fixed. Then what about the position of the particle? It may go from minus infinite to plus infinity. Once if you are able to measure the momentum accurately, you cannot measure the position. Inaccuracy in the position will tend to infinite. So, uh, if you add so many sine wave, that you know, then you will get a wave packet. You have studied the wave packet already. So, you know the wave packet. So, if you join the envelope of wave packet, it is Gaussian like things. So, here you are adding more and more frequency. That means different energy, sine wave of different energy. You are adding sine wave of different energy. Uh, but you are trying to localize this. when you add so many frequency, of course, I have drawn this diagram, enlarged version. If you keep on adding the sine wave, it will become narrow and narrower. That means when you are adding a different frequency, that is a different momentum, you cannot measure the momentum accurately in this case. However, you can measure the position accurately. This is about the uncertainty principle. Uh, in a generalized statement, you cannot measure two canonically conjugated parameter uh, accurate simultaneously accurately. We will see in detail with the proof. Now we will see the proof for generalized uncertainty principle. From point of view of standard deviation, uh, delta A cat, this is A is an operator, delta A, error involved in delta A is equal to A minus the average value of A. Here in quantum mechanics, it is the expectation value of the operator A. Similarly for P, delta P is equal to P minus expectation value of P. So now you consider the operator A. Then if you square it, delta A square is equal to A square plus B square. That is expectation value of A square plus 2AP. Using that formula, that is A plus B squared is equal to A squared plus B squared minus 2AP. 2A P is the expectation value of the A. Now, uh, uh, now what is the expectation value of delta A squared? Then by definition, this is inner product with A squared, operator A squared. That is psi A squared psi. By definition, it is the expectation value of the operator A squared. Here it is minus 2 expectation value of A. A is a number because it's a expectation value, so you can take outside. 2 also number, you can take 2 times the expectation value of A and the inner product of A. So this is because here you have one A. So you have to take the inner product in order to get the expectation value. The third term is already is a expectation value of the square of the expectation value of A. So this is the number. So you need not take inner product. Even if you take the inner product, since it's a number, you can take out of the inner product. So psi inner product of psi with the psi will become 1. So this will be retained as square of the expectation value of the A. Then we will see this one. This one is nothing but the expectation value of A squared minus this is 2A. This is nothing but the again the expectation value of A. So expectation value of A into expectation value of A is expectation value of A squared. Here already we have expectation value of A squared. So that is the reason why I have mentioned this in the red color bond. So if you take second and third term, this will become minus because this is 2 expectation value of A squared plus A squared will become minus the expectation value of A squared. This is the expectation, sorry, this is the expectation value of A uh, power whole square. This is the expectation value of A squared. So, the expectation value of A squared minus expectation value of A whole squared is nothing but your variance. In the point of view of standard deviation, it is nothing but the variance. Now, in the statistical point of view, the variance of the operator A, that is sigma A squared, is equal to the expectation value of delta A square, which is equal to expectation value of A square minus expectation value of A whole square. Similarly, for delta P, operator P, that is here sigma P square. From Cauchy-South inequality, we know that the expectation value of A squared into expectation value of P squared is equal to or greater than the modulus of the expectation value of delta A into delta P whole square. This is the Cauchy-Schwarz inequality. Now you just take the right hand side without square. That is the expectation value of delta A into delta P. We will try to simplify this. So if you take the right hand side, that is expectation value of delta A into delta P, which is equal to half the expectation value of commutation of delta A delta P plus of the anti-commutation of delta A into delta A with delta P. Now, if you expand this first term, delta, that is commutation relation, delta A is which is equal to the delta A delta P minus delta P delta A. Similarly, this is anti-commutation relation. This can be written as delta A into delta P plus delta P into delta A. Here, see, I have mentioned a red color point, second term, in the here as well as here, second and fourth term. This is minus, this is plus. So, both will get cancelled. And this is of delta A into delta P. This is of delta A into delta P, which will become delta A into delta P. So we have taken the right hand side and we have expanded like this. So there is no difference between this and this. We have seen. So delta A into delta P can be written as like this. That is expectation value of delta A into delta P can be written as of expectation value of commutation of delta A with delta P and plus of expectation value of anti-commutation of delta A with delta P. So these two are equivalent. Now we will see according to Cauchy's inequality. So we have seen that the expectation value of delta A into delta P is equal to of the expectation value of commutation of delta A with delta P plus of the commit expectation value of anti-commutation of delta A with delta P. Here you take the first term, that is commutation of delta A with delta P. So delta A, you know, A minus expectation value of A. Delta P is equal to P minus expectation value of P by definition. Here I have made the delta A, sorry, expectation value of A and expectation value of P in red color. You know, the expectation value is merely a number. So any two number will uh, commit. Also, any constant value or any number will commit with any operator. So we can ignore the numbers, that is expectation value of A and P. The only non-committing terms are A and P. So the commutation of delta A with delta P can be written as the commutation of A with P. So this is the conclusion we arrived. So you replace this in the first term here. So this will become of expectation value of commutation of A with P instead of delta A with delta P plus second term you keep as it is. Okay. Here Another interesting thing is, this is one of the interesting thing, that is commutation of delta A with delta P is equal to commutation of A with P. So that is one important thing. Another important thing is, any quantum mechanical operator is a Hermitian operator. So in that case, A is a Hermitian operator as well as P also a Hermitian operator individually. But the commutation of A with P is not a Hermitian. It is anti-Hermitian. You can check within one or two steps. It is very simple. You can prove very easily within no time. Similarly, the anti-Hermitian sorry, anti-commutation relation gives you the Hermitian operator. Uh, that also you can prove within no time. It's a very simple proof. I don't want to do it here. Since the commutation of two operator is anti-Hermitian, it is imaginary naturally. So that is the reason why I have introduced modulus here. So if you take modulus of expectation value of delta A into delta P whole square is equal to half will become 1 by 4, and this modulus of commutation of A with P whole square plus this p squared, that is modulus of 1 over 4 1 over 4 modulus of expectation value of anti-commutation of delta A with delta P whole square. Here it is important to note that I have ignored the cross term, that is a plus b whole squared is equal to a squared plus b squared plus 2ab. 2ab means a is this one, b is this one. This is cross term. One is commutation relation, another one is anti-commutation cross term, which will get cancelled. I have ignored the cross term. I have taken only the first term and the second one, that is a squared plus b squared. I have ignored 2ab because it is a cross term which will get cancelled. And one more important point is, comparing a b, delta A, delta P is very small, and if you take square, still smaller. So I can cancel this one. I can cancel the second term. Now, the modulus square of the expectation value of delta A into delta P is equal to 1 over 4, the modulus of expectation value of A with P whole square. So we got the relation that modulus modulus the expectation value of delta A into delta P whole square is equal to 1 over 4 modulus square of the expectation value of commutation of A with P. According to Cauchy-Schwarz inequality, uh, expectation value of delta A squared into the expectation value of delta P squared is equal to or greater than modulus square of the expectation value of delta A into delta P. Then you know delta A into delta P whole square expectation value. You can replace this by just now we got this 1 over 4 modulus square of the expectation value of the commutation of the A with P. So if you take the square root, you will get delta A expectation value of delta A into expectation value of delta P is equal to or greater than 1 over 2, because we are taking square root 1 over 2 the expectation value of commutation of A with P. So now we got that the expectation value of delta A into the expectation value of delta P is equal to or greater than of modulus the expectation value of commutation of A with P. So this is the generalized uncertainty principle. Now we will apply this to this part, position and momentum. Let us say the operator A is the position operator and operator P is the momentum operator. Then delta x in expectation value of delta x into expectation value of delta P will become equal to or greater than half the modulus of the expectation value of commutation of x with p. So you know very well the commutation of x with p is I h cross. Since it's a modulus, you can ignore I, so this will become h cross alone. So now your delta x into delta p is equal to or greater than h cross by 2. Here we will see some interesting factor. See, H cross is itself is a very small number. It's in the order of 10 power minus 34. Then what is the meaning of dividing this by 2? It has some physical significance because dividing by 2 will not make much difference. However, you know very well that 0 point energy is half h cross omega. So this is the minimum error you can identify. If you multiply this by omega here, by omega h cross omega by 2, that is half h cross omega. So that is the minimum energy. That is the reason why we have introduced off here. So this is the minimum error after. So in similar way, you can find the uncertainty principle for energy and time. This is the generalized uncertainty principle. Thank you very much for watching my videos and supporting me continuously. If you have any question, kindly send to me the following mail ID vasumku@gmail.com. I will answer at the earliest through mail or YouTube videos. My YouTube channel ID is www.youtube.com/c/vasuvphysics. Thank you for watching my videos.